Okay, so for 4.1b, there's 3 terms that are really critical. So we're on our critical terms and ideas. The 3 terms we're looking at today are sine diagram, zeros of a polynomial, and multiplicity. Okay, so we're still working on polynomials, and we use a sine diagram often is a really great tool for sketching the outcomes of a polynomial, the outputs of a polynomial, whether it's a negative or it's a 0 or if it's a positive. We don't get really crazy about the accuracy of the sketch, just the behaviors of the graph. When is it producing negatives? When is it producing zeros? When is it producing positives? And that's what the sine diagram helps us do. So sine diagram is a compact tool, easy to use once you learn to use it, that conveniently presents a way to see the intervals over which a polynomial produces negatives, zeros, and positive results. Note, if a poly is factored completely, we can more quickly use the product of factors to find positive and negative results. Sometimes it's impossible to factor. Some polynomials are really hard to factor, but we're going to give it a go anyway. Helpful tip, anytime you have a quantity, a factor, that's a squared factor, or even if it's a fourth powered factor, or if the exponent is even, it's going to produce positive outputs only, right? It doesn't matter if I'm taking -2 and I'm squaring it, that's positive, or +2 and squaring it. If I take -2 to the fourth power, that'll be a positive. So anytime you raise a negative value to a positive exponent, or I mean an even exponent, you're going to get a positive. So that's just a little tip. All right, so let's do a sine diagram. Let's say that we have this equation factored out. The f of x is equal to x squared times x minus 2 times x plus 3. Well, when an equation is factored out, it's really easy to see where the zeros are produced. All you have to do is set each of those quantities that contain an x equal to 0. So this would be x equals 0 because 0 squared is 0. This would be x equals 2. Right? 2 minus 2 is 0. And this would be x equals -3. So if I were creating a sine diagram, what I do is I create my x-axis and I plot my 3 zeros. In this case, there are 3. So -3, 0, and 2. And then what I do is I take my factored forms, x squared, x minus 2, and x plus 3. Those are my factors, the things I'm multiplying together. And all I do is I create an input and output. So what makes x squared 0 is 0. 0 squared is 0. And regardless, if I take a -4 and plug that in, -4 squared is +16. If I plug in a number here like -2, -2 squared is +4. If I plug in a 1, 1 squared is +1. And we're just trying to get positive and negative outputs. I don't even care what the actual values are. I just want to know if they're positive or negative. If I plug in a 3, 3 squared is 9. That's positive. So like I said, quantity squareds are always going to produce positives unless, let's go back, unless it's a 0. 0 squared produces a 0, but all of the other numbers squared are going to produce positives. So let's do positives or zeros only. That should have been what I wrote there. Okay, so there's x squared is always going to produce either a 0 or positives. Now x minus 2, 2 minus 2 produces a 0. So any number to the left of that is going to produce a negative. Like if I plug in a -4, that's -6, right? And anything to the right of that 0, if I plug in a 3, 3 minus 2 is 1, will produce a positive. So that's what's going to happen on my domain. If I'm less than 2, I get a negative for x minus 2, and if I'm right of 2, then I get a positive. For x minus 3, -3 is your 0. So to the left of that, you would get a negative, and to the right, you would get these positive values if you're picking numbers on your domain. So now what we're doing is we're multiplying these 3 signs because this is a multiplication problem up here. You're doing x squared times x minus 2 times x plus 3. So we're going to multiply. Positive times negative is negative times negative is positive. So that means anything in this section of our domain is going to be above the x-axis. At x equals 3, you're going to have a 0, because 0 times negative times positive is 0. So that's 0. Here you have a positive times a negative times a positive. In this section, that's going to produce a negative. So this means you're going to be below the x-axis. Here at x equals 0, you have 0 times negative times positive. That's 0. In this next section, look at here, you have positive times positive. That's negative. So your graph is going to be below. And then here at x equals 2, you get 0 times positive. That's a 0. And then at 3, positive times positive is positive. So now you're going to be above the graph again. So what would this graph possibly look like? Now I'm just going to sketch it. And I have a 0 here at negative 3. So my graph is going to cross there. A 0 at 2, a 0, and a 0 at 2. All right? And to the left of 3, my graph is going to be above the x-axis. Between 3 and 0, I'm below, so I'm going to go negative, and then I'm going to come back up to my 0 here. And then between 0 and 2, I'm back below, so I'm going to bump off of the 0. And then I'm going to be below. Between 0 and 2, I'm below. And then after 2, I'm above. So the graph looks something like that. Notice that I didn't put I didn't put a scale on my y-axis. I don't want to do that. Okay, so you can see to the left of 3, I'm above the x-axis. At negative 3, excuse me, to the left of negative 3, I'm above. At negative 3, I'm at 0. Between negative 3 and 0, I'm below the graph because it's producing a negative output. Then I'm at 0. Then I'm below again, and then I'm at 2. Now let's go graph this in Desmos, and let's see how close we got. Let's see how close our diagram got us to the graph. All right, so let me get that out of there. And so that one was y equals x squared times x minus 2 times x plus 3. All right, let's take a look at our graph. So that's the shape of our graph. It's a little dramatic, like these points down here, but notice we didn't put a scale on our y-axis. We did not put a scale on it, so we're good. That's what we did. It was a little more dramatic. Maybe it looks a little better if I do that, because there's a bigger gap between negative 3 and 0 than there is between 0 and 2, and that's something to put into your thoughts when you're doing it. But that's how you use the sine diagram. And now if I were going to write this, I would say that the f of x is greater than 0 in the intervals between negative infinity and negative 3 and 2 to infinity. That's when I'm above the x-axis. And the f of x is less than 0 or below the x-axis in the intervals between negative 3 and 0. Not at 0 though, and then 0 and 2. And so those are also things that I might ask you to look at with your sine diagram. And you can just see it here. You don't even have to graph it to see when you're above and below, when you're positive and you're negative. So there's a sine diagram. All right, let's move down to zeros. Zeros, sometimes called roots, are the solutions of the equation y equals 0, f of x equals 0. Each real 0 is an x-intercept. That's another number or another word. So zeros are roots, they're x-intercepts. Sometimes they're called solutions. Okay, so it has 4 words, or four names. Zeros can be real or imaginary. If they're real, they're an x-intercept. If they're imaginary, they don't cross the x-axis. They can be positive or negative. They can be rational or irrational. They can be large or small. And many times they're difficult to find. Therefore, we use calculators. All right, important. Imaginary zeros come in pairs. Imaginary zeros come in pairs, and we'll look at that later. But what's really important here is the tip here, that if you can factor to find zeros, that'll really help you out. All right, so let's say that I have this function here. The f of x is equal to 2/3 x cubed plus 8x squared minus 2/3 x plus minus 8. All right? So I don't have that factored out, and that would be really difficult for you to factor out. Actually, I do have it factored out. It would be really difficult for you to factor out, so I'm going to put it in its factored form. It is 2/3 times x plus 12 times x minus 1 times x plus 1. So this is the factored form of this function, and it is a beast. But what are its zeros? This is what I'm concerned about. What are its zeros? Okay, so its zeros are negative 12, right? X negative 12 plus 12 is 0. And then plus and minus 1. So a positive 1 and a negative 1. Now, those are our zeros. So if I were to graph this, its zeros would be here at negative 12 and negative 1 and 1. And those would be the zeros. And of course we could use a sine diagram to figure out when we were above or below. But I think the big point here is that when you can factor to find zeros, that's useful. Another thing you can do to find zeros is to type it into Desmos or your graphing calculator. So I'm going to do that one more time. So this was f of x. I'm just going to write it as y equals 2/3 x cubed plus 8x squared minus 2/3 x minus 8. And you can see here your zeros are at negative 12, 0, negative 1, 0, and 1, 0. And so that's an easy, that's better when these functions are really difficult to factor. You can use your graphing calculator to help you determine where the zeros are. So that's useful to know. Okay, the last term I want to talk about is multiplicity. Multiplicity is a multiple. It means more than one. If something has a multiplicity of 2, it means it happens twice. Or if it has a multiplicity of 3, it happens 3 times. So a 0 or a root, 0 is the term I prefer, of multiplicity m. Okay, a 0 that occurs more than once in y equals 0, or f of x equals 0. And this formal definition is just horrible, but we're going to go ahead and give it to you. C is a real 0. It should say if C is a real 0 of the f of x of multiplicity m, then the f of x has a linear factor x minus c to the m power. So it's the power. That's the power. The power is the multiplicity, and the graph of the function has an x-intercept at the 0, whatever c is. So some things to note. If your multiplicity is even, the graph bounces off the 0. If the multiplicity is odd, the graph passes through. Odd multiplicity, the graph passes through the 0. And also, the higher the multiplicity, the flatter the graph gets at that 0. So I'm going to actually scooch that over. Let me get rid of that. So if the multiplicity is even, the graph bounces off the 0. And if the multiplicity is odd, if the exponent is odd, the multiplicity will pass through. But like I said, if the multiplicity, the larger the multiplicity, the flatter the graph will get around the 0. So I'm going to give you a demonstration here. So let me just pull up my note page here so I can see. Where's my multiplicity? Okay, so let's say we have this function, f of x equals 1/16 times x minus 2 times x minus 4 cubed times x plus 1 squared. Okay, so our zeros are 2, and it has a multiplicity of 1 because it's being raised to the first power. And then we have a 0 at 4, and it has a multiplicity of 3. So these are our odd multiplicities. So the graph is going to pass through these zeros, and it's going to go from positive to negative or negative to positive. And then you have this last one here. This is 0 of -1, and it has a multiplicity of 2, which is an even. So the graph is going to bounce off of that 0. So I'm just going to draw the picture for you so you can see it. It looks something like this. So here at -1, and then at 2, and at 4, you have zeros. And then I'm going to go ahead and graph this for you. It's also going to pass through x equals 8. And how I found that, that's the y-intercept, because I'm just plug zeros in here and here and here. Then I multiply 1/16 by all those numbers, and this is my output. We're not worried about that right now. So the graph does this. It goes like this, and then it bounces off the -1 because it has a multiplicity of 2. So it starts positive, and then it hits -1, and then it goes back up to positive because of that even multiplicity. And then it's going to come up like this, and then it's going to pass through 2 pretty steeply because it has a multiplicity of 1, and then it's going to come back up through 4. 4 has a multiplicity of 3, so that's odd, so it's going to pass through, but as it gets closer to 4, what it's going to do is kind of flatten out near the 0, so it looks something like that. So I'm going to fix that up a little bit. So that is similar to what that graph would look like. So zeros and multiplicities. The exponent is the multiplicity. Remember, if it's an odd multiplicity, then the graph passes through the 0 from positive side to the negative side, or vice versa. If the multiplicity is even, the graph will bounce off of the 0 and go back in the direction in which it came. So I'm going to show you this function in Desmos as well. So this one would look like y equals 1/16 times, let's see, what was it? X minus 2 times x minus 4 quantity cubed times x plus 1 quantity squared. Oh, I forgot the x. Let me get the x in there. X plus 1 quantity squared. All right, so let's take a look at our graph. So you can see your zeros there, there, and there. There's my y-intercept. Well, I didn't do an awesome job drawing it, but you can see passing through x equals 2. That had a multiplicity of 1, so the graph, as it passes through 2, it's going from the positive side to the negative side, and it's going pretty steeply. But as I come back and I approach x equals 4, because 4 had a multiplicity of 3, see how the graph got kind of flat right around that 0? That's supposed to happen. So that's multiplicity. So that's the end of that lesson. And now we're going to start the lesson for 4.1b.